Okay, good afternoon. Merhaba. Son 2 gündür bu kadar zevkli bir zaman geçirmedim. Let me go back to English again. I thank to all organizers, I thank to all of you making this beautiful time. I am really amazed that I could feel that much at home here. With so many mechanical engineering students, and it one of the things that was surprising me, there was so much enthusiasm. So indeed, this fits very well to the theme of my presentation. Um, I will tell you about mechanical engineering, but the most important thing, I'm not just going to talk about what mechanical engineers do or what they should be doing, but I will tell you a personal story of what I have done. I was about your age when I graduated from mechanical engineering. Since then, the things that I have done was surprising. Um, this morning, Dr. Barabas mentioned mining engineering is very important. I agree with him that everything should come out of earth and they should mine this very carefully. But then the mechanical engineers do everything around you. So all of the departments, all of the disciplines are important, and I am emphasizing that they should work together now. But now I'll get into the mechanical engineering and I'll give you a personal story. First of all, it's radiation transfer. It is not nuclear radiation, it's heat transfer. Heat transfer is one of the two important areas in mechanical engineering. Heat, you process, and then of course mechanical systems. Usually mechanical engineering disciplines divided between thermal science and mechanical systems. And among the thermal systems, you have conduction, convection, and radiation. Of course, there's boiling as well. That's the radiation transfer I'm talking about. It's light. And light has been my passion all my life. I enjoy light, I enjoy photography, I enjoy lasers, and I enjoy all kinds of things that light do, or derivative of light do. So that's what I'm going to talk about. This photograph is not that clear because of the light, but you must see the light. It's Istanbul. I came to Istanbul about 10 years ago, after living half of my life in the United States. So in this graphic, I'll show you that I left University of Kentucky back in 2008, and I had a major laboratory there, radiation transfer laboratory. I will tell you some of the research that came out of that. And then I moved to Özyeğin University as one of the founding members of the university. I started the mechanical engineering program there from zero. There were no students, no faculty members, no library, no building, no program at all. And then since then, mechanical engineering became a very nice department, one of the best in Turkey. And then we established the Center for Energy, Environment and Economy. Whatever you do, you must start with passion. You must have an overreaching goal in life. And one of the biggest concerns we have is the climate change, of course. Now, you can ask what's going on with the climate change and mechanical engineer. Almost everything we do, if we use the resources efficiently, effectively, you become a good engineer and you can fight against all kinds of problems. And of course, climate change is a huge problem. It cannot be solved overnight, but this is one of the issues. What can you do with that? You can decrease the density of energy used per person. That means you have to be a very good engineer to do whatever you do with less energy, less fuel, less materials, less resources, less time. Show yourself, show your smartness. Decrease the time, resource, and everything So you can come out with better world. This picture, I'm not sure if you see it clearly, but it shows one of the problems. When you burn things, you pollute. But we have to burn, otherwise we cannot have the light, or we cannot have my sound coming to you. Yet you can ask the question, do we need this much light, or do we need this much material? Well, if I look at the previous slide, then if I try to understand what's going on, I must get into the science of everything. Science is the most critical. So if you are studying any discipline, first you have to get into the science, mathematics, physics, chemistry, and then combination of these, dynamics, controls, mechanics, artificial intelligence, and go on, networks. When I look at the atmosphere, when I see what happens to sun when it arrives to Earth, there's a very thin layer of atmosphere and everything takes place there. You see all kinds of heat transfer mechanisms and atmospheric interactions of the light with the particles and so on. So you have to understand, and they are all part of radiation transfer. One thing was not mentioned, and most of the atmospheric science literature talk about everything else, but then there are buildings. The buildings and the cities we built over the years make the life more complicated. So you have to understand also what happens to the buildings. So with this idea, again, you can get into the details. I'll show you these slides very rapidly because I have several slides and I would like to ask you, please warn me 5 minutes before it's over so I can stop. Otherwise, I can talk like hours. But when you get into the heat transfer or the details of chemistry, you can quantify. All these numbers require that you have to make some measurements. So measurements, understanding, interpretation, and then now big data, the artificial intelligence, neural networks, augmented reality, all of these will help you to understand all these physical phenomena so you can really improve your skills. Then what happens? Probably many of you know, I'm not sure if you can read this one, but this shows what type of energy resources are available on this side and where we use them. Let me explain to you a little bit simpler. This side, you have coal, petroleum, natural gas, solar energy, wind energy, and everything. Being in Baku, in Azerbaijan, you can imagine too, there's about 50%, 60% of all energy we use all over the world come from the fossil fuels, and of course from Azerbaijan. All of them are mined. Coal is mined. Will they change? No. In the next 30, 40, 50 years, it's not going to change much. Maybe sun will be like 10%, 20%, but that's it. Most of it will stay here. So, if you are going to make an impact on climate change and other things, you have to minimize their use. We cannot give up from these things, but we use them for buildings, for transportation, for industry, and for agriculture. Buildings, industry, and transportation each take about 30% each, and then 10% is left to the agriculture. So I need to do something about this part. So when you do it, you just focus on your objective. So you have to come out with, again, the goal. So in this case, we looked at the production mechanisms, which is part of the mechanical engineering. We also try to understand how we can minimize the use with efficient cars, efficient buildings, and the industrial systems. With this idea, we established the center. In the middle of this, you see the climate change and living with nature in harmony. And to be able to do that, you have to come out with really scientific research, and all these small areas are funded research topics in the center. And most of it is related to radiation transfer. And if you get into details, you have to look at energy harvesting, buildings, industrial applications, and the cities to make the cities more livable and so on. Look at this picture and think about, and mechanical engineering is telling this to you. When you think about typical mechanical engineering, you may not hear any of these things. But I feel like I can contribute to all of them. So that's the reason, in addition to Dr. Barbas, I'm insisting that mechanical engineers are also the mother of all engineers. He was claiming mining engineering is the case. So you can do lots of things with mechanical engineering. Of course, you have to work together with all other disciplines. When I came to Istanbul 10 years ago, there was nothing, as I mentioned to you. Our team is now like this. We had several of them graduated, but we have more than 20, 25 people. We had several European Union grants, FP7, Horizon 2020, and Turkish grants. It's a very active program. Let me start. I said that we have to start from fundamentals. Now I'll go fast. When you look at radiation transfer, you look at the energy exchange between a hot object and a cold object. From hot object to cold object, the light moves, energy moves. It's thermodynamics. It's a matter of understanding thermodynamics, which is essential for mechanical engineering as well. There, you need to look at the different parts, how the light interacts with anything. When you start from there, you find out that these ideas are not new. I insist that I keep telling this to myself as well as to my students. We are not the smartest people on earth. We always find somebody else who have done lots of good things. When I say the exchange of energy between anything, and if you go back, one of the amazing guys is the Archimedes. Archimedes, he lived in Sicily about 2,200 years ago, and he used the idea of solar light to burn the ships of a Persian navy. At that time, he put the mirrors on the shore, he aligned them, and everything came onto the ship, and he burned. It's understanding how the light is transferred. I'm not going to talk about others, but when you start this, you have to go to understanding of the fundamental relationships. It requires mathematics. Then a little bit deeper mathematics. You combine all of them to come to the concentrating solar power systems. We discuss many of these ideas in a book. This is one of the books that I co-authored on radiation heat transfer. It is one of the best known books in the world. So we discuss all these things. Once you start from there, you try to understand why something emits energy, so why something else absorbs energy. The fundamentals of this is also given by another big guy. He's Planck. Planck is a German guy. When he came out with this correlation, how he can understand the emission from radiation and then absorption, eventually he led the way to open the quantum mechanics. This goes to quantum mechanics. I'm not going to get into details of it, but it is, again, the theory of heat radiation, and the Planck constant is well known now. If you continue, it's not over yet. So it's not just two expressions or a couple of calculations. You have to look at the spectral effects, directional effects, temporal effects, coherent effects, all of these. The books are a lot. So the reason I show these slides, there will be a few more of these, that you will never be done with your studies. You should continue learning more. More information is available there. And the science requires you to get into depth of all these analysis. There are several books. If we look at how we impact the industry with this know-how, we can look at some of the things. This is one of the work that we have done long time ago to understand the coal combustion in a furnace. The coal-fired burners, power plants are very expensive. They are very, very difficult, intricate systems, and they burn coal inefficiently. So if you understand science, you can do something about it. So it's a huge system. There, you have to solve the radiative transfer equation. After that, you can look at all other things. You can apply the radiation transfer to other industrial processes. You can understand how the glass is made, how you can handle the transportation of energy, how you can minimize the systems that's used. And then you can apply this continuously to any kind of system. And one of the techniques I mentioned here is the Monte Carlo. Suddenly, I go from physics to mathematics. And this is the bottom line in science, in mechanical engineering, or in any discipline. You have to give emphasis on the physics. Physics is the key, because that allows you to read the nature. And then you go to the mathematics to simulate it, the computational tools to simulate it faster. Then you have to go back to physics to see if you understood what's going on. And then to speed up, that's what we are using now. We are integrating Monte Carlo with the hardware to make it faster and faster. On the other hand, when you look at coal, you have to understand how the coal behaves when it sees the light. This means you have to look at the particle properties. There are all kinds of particles like that. Each one of them is smaller than the thickness of your hair. All these things are discussed again in so many books. So this is the beauty of science. You should be going back to library or keep buying books for yourself. And this is one of the things that we studied, interaction of the particle clouds and the light. I don't know why this slide doesn't show, but we came out with the equipment. And this equipment, this graphic, okay, it's not available. We got a patent with a PhD student. This is a laboratory version of it. Eventually, we built a desktop unit, and we sold it to Horiba, Japan. Horiba is one of the biggest particle characterization companies in the world, along with Malvern and a few others. And it's the first time they bought a patent from outside Japan. This was about 10 years ago. And this got an R&D 100 award. But think about it. We are measuring how these particles are behaving, or how big they are, what shape they are. But at the end, you have to come out with a machine. This is the mechanical engineering. So you have to understand how the concept is supposed to work, what purpose it's going to do, work, and then you have to come out with the machine itself. If you continue now at the realm, you find out that you can reach to nanoscales. Again, nano, if you take the thickness of if you take a hair from your head, its thickness about 100 micrometer. If you cut it 1,000 times, you are at 100 nanometer. It's not still nanotechnology realm. You have to come to 10, 20 nanometer. So how are you going to see those things at 10, 20 nanometer? Again, there are zillions of books, not zillions, 10, 15, because this is a new area in the last 10, 15 years. But seeing those nanoparticles, indeed, we have been doing it. Probably all of you know about this. Yesterday, we were at the Carpet Museum, and they were showing those stained glass windows. All those colors come due to the different size nanoparticles being in some kind of substrate. So, depending on the shape of the particles or size of particles, you get different colors. Good. This was mixed. So the question is, if I'm a mechanical engineer, if I'm a chemical engineer, I mix them. Don't get offended with that. But if I become a better engineer, I decide what to do with the size of the particles and how I change their performance. So if I look at what's going on, for example, on a surface, if there's a particle, a nanoparticle, I look at how the light comes and interacts with that and reflect it. Or if I bring two surfaces close enough, the gap is less than 10, 20 nanometer, what will happen to that? And suddenly, you begin to hear words that almost no mechanical engineering undergraduate student hear. They are called plasmonic, phononic, photonic interactions. So suddenly, you have to think about what plasmon is. Plasmon is electron cloud. Phononic is lattice effects. So you have to understand the electron behavior and lattice behavior. If you begin to go into that, you can think about machining, which is mechanical engineering word. At nanoscale, if you use the plasmonic effects and phononic effects, this is one thing that we have done, again, with another PhD student, Eli House, about 10 years ago. We were able to melt either silver or gold particles independently. So you bring an atomic force microscopy tip on a surface when there are gold or silver particles. Depending on the light or interaction, the gap distance between them, you can either melt the gold particles to each other or silver particles to each other. With this, you are able to write things. With that idea, we came out with another experimental system. Look at this. This is a beautiful machine. It worked. It is to see those 10, 20 nanometer nanoparticles on the surface of a substrate, of a glass. So again, this goes from physics to measurements and then to mechanical engineering. If you continue, then the next question you can ask, okay, if I bring these surfaces together, can I transfer energy a little bit faster? We started, well, I don't know why these slides are not showing, but when we started that, another PhD student in Kentucky, we developed the tools. It was completely computational tools. He's a professor now at the University of Utah. And recently, with another student in Turkey, and as a matter of fact, an Iranian student, she completed her PhD under me, and now she's an assistant professor at another Turkish university. And with her, we looked at the nanoparticles with the gaps, with the holes, with the bumps on top of each other. What's the use of these? When you get in there, you begin to see that similar structures, very similar structures, are available in nature, especially in morpho butterflies. These beautiful blue butterfly you see, the colors are not because of pigments, but it's because of the nanostructures it has. So using those nanostructures and making the simulations like that, we find out that at certain wavelengths, we can increase the energy transfer in order of 10 to the 10 times, or sometimes 10 to the 5 times, 100,000 times. This allows us to come out with new type of sensors or radiative cooling mechanisms. And with some of the machining, we wrote another book with another PhD student. He's from Malaysia. Now he's a professor in Kuala Lumpur. We looked at the electron beam-based manufacturing. And for that, we looked at the machines and we tried to see if we can come out with the new type of machining procedure. Just to give you an idea, and it requires, again, writing new type of codes for radiative transfer, electron transport, and sound transport. Recently, we looked at the buildings, and again, in the beginning I mentioned to you, and in Istanbul we played with the buildings a lot, but again, we found out that we are not the smartest person on earth. One of the people I admire is Vitruvius. Vitruvius is a Roman architect. He was the architect of Rome 2,000 years ago, and he had a book, 10 books on architecture. When I started reading his book, I realized that he was a mechanical engineer. Of course, at that time, there was no mechanical engineering, but everything we do is, almost everything is given in his book. So we used some of the concepts he had, the most important, and I think this applies to you. We insisted on making architects and engineers to work together. And then we continue with our work on engineering, and we use the radiation transfer to come out with the spectral effects. This is the spectrum, wavelength versus energy, and emissivity, how much it's reflected or so on, and coming out with different type of materials laden with different type of particles to change the emissivity of the building surfaces, so the buildings, even when they are exposed to sun, can cool down. Not can warm up, but can cool down. It's called radiative cooling. It's from completely different perspective. With few other students, we look at the visual comfort, how good you can read under this light, whether you need this much light or not. Again, going back to history, this is a picture of Hagia Sophia in Istanbul. Look at how beautiful it's illuminated. And we can make the calculations now to see how much glare is available, how much intensity is available, based on the windows and artificial lighting. And we applied some of these in our buildings in the university, which made one of the university buildings the most energy efficient university building in Turkey. We applied this to 2 campuses. One of them is our campus. Look at this picture. 7 years ago, there was nothing there. There was no view. This campus was not available. Now it's the most sustainable campus, sustainable energy campus in Turkey, and most sustainable campus as well. The other one is we are building 2 football field size fields with solar concentrating power systems. This is going to be one of the largest in Europe. This is with another European Union grant. Again, thank you for listening to me. The message I give you is there's lots to do, especially when you are work as a team, when you work with other disciplines. And I liked today's team, and I mentioned to the organizers, to Anwar and everybody else who's worked with him, Anwar, Eli, and so on. This is really a great starting point. If you want to find something else about mechanical engineering or center, you can send me a note. Thank you for listening to me.